Greetings and welcome to episode 1 of the Math Olympiad Senior Lecture Series. This video is targeted at 15 to 16-year-old students taking the SMO or the Singapore Math Olympiad, which is why I've curated 10 of the past year Olympiad questions for your exercise. I've also labeled this Part A just in case I have more time in the future to add more logarithm questions later, and they'll be titled 1B and so on. So for this first lecture, we're going to be just focusing on logarithms. So in case you missed it, I've just done a 4-part O-level series on logarithms, which will give you a basic grasp on logarithms. So in it, we look at how to convert indices into logarithms. We looked at the 5 laws of logarithms from the product law, the quotient law, the power law, the change of base law, and the reciprocal law. These were very helpful for solving basic indice and logarithmic equations. Then we ended on modeling as well as sketching of log graphs. Like this is the graph of y equals to log base a of x for a greater than 1. Let's take a look at question 1, which is taken from SMO 2018 Senior Section question 4. Which of the following is the largest? Is it log base 5 of 7 minus log base 5 of 6? Or log base 6 of 8 minus log base 6 of 7? And these options continue until log base 9 of 11 minus log base 9 of 10. Pause the video here and give this question a good try. Now in order to solve this question, we need the graph of log base 5 of x. What is the physical representation of log base 5 of 7 minus log base 5 of 6? It is actually the height of this green triangle with a unit base, and this is clearly taller than this blue triangle, which represents log base 5 of 8 minus log base 5 of 7. And that's quite close to option B. But where does option B lie? Well, we need the graph of log base 6 of x, shown by this purple line, which is a squished up version of the blue graph. And I've exaggerated the squishing to make it a little bit more obvious. So option B is this red triangle, the height of this red triangle. And you can see that the green triangle is taller than the blue triangle, which is taller than the red triangle. Hence option A is bigger than option B. So we can eliminate option B. And by this same argument, we can also show that B is greater than C, C is greater than D, and D is greater than E. Hence, the answer will be option A. So did you get the answer? Question 2. Which of the following is the smallest? Pause the video here and give this question a good try. So we can consider the function log base x of x plus 1. Apply the change of base law to the natural log. This will give us ln of x plus 1 over ln x. And we can differentiate this using the quotient law. Looks quite messy, but we can simplify this. In the denominator, we have ln x squared, and we know that this is always positive. We'll have x times x plus 1. And this will be positive for x greater than 0. And in our case here, our x is at least 2015. So this is going to be, the denominator is something that's always positive. So let's look at the numerator. We have ln x to the power of x minus ln x plus 1 to the power of x plus 1. And x to the power of x is an increasing function. Hence, ln of x plus 1 to the power of x plus 1 is going to be larger than ln of x to the power of x, since log itself is also an increasing function. So in our numerator, we can see that we're going to get a negative result since the second term is larger than the first term. That means this entire gradient function, this dy dx, is going to be negative. So we're getting a decreasing function. So as x increases, the function decreases. So our answer will be option E. So did you get the answer? Moving on to question 3. How many positive integers do not satisfy the inequality n to the power of 1/3 of log base 20 of n greater than the square root of n? Pause the video here and give this question a good try. Now what we can do is we can convert square root of n to n to the power of half. Now that we have the same base, we can compare the indices, telling us that 1/3 log base 20 of n is greater than half. Multiply by 3 on both sides, and converting this log into an indice, we know that n must be greater than 20 to the power of 3 over 2. Now it's not easy to work out what is 20 to the power of 3 over 2 without a calculator, but if we square both sides, what we're actually looking for is n squares that are greater than 8,000. But that's not the question. We are looking for things that do not satisfy this. So we want n squares that are not bigger than 8,000. So let's look at possibilities. If we consider 90 square, that's 8,100, which satisfies, and we don't want satisfy, we want do not satisfy. If we look at 89 square is 7,921. It does not satisfy, so that's what we want. So 89 and every positive integer before 89 would not satisfy this inequality. Hence, the final answer is 89. So did you get this answer? Question 4. Find the value of 2021 to the power of log base 2021 of 2020 multiplied by log base 2020 of 2019 multiplied by log base 2019 of 2018. So pause the video here and give this question a good try. So this is quite an easy one. We just need to consider the power. We can apply the change of base law. Let's change it all to the natural log. So I have ln 2020 over ln 2021 multiplied and so on. This gives us things to cancel out, and we can convert this back into its log form. So we do the change of base in reverse. We get log base 2021 of 2018, and we sub that back as the indice. You see that you have 2021 to the power of log base 2021, and those two things will cancel out since 2021 to the power of something and log base 2021 are inverse functions. We'll get 2018 as the final answer. So were you able to get it? Question number 4. Let x be the integer such that x is equals to 5 to the power of square root of 2 plus 4 times log base x of 5. Determine the value of x. Pause the video here and give this question a good try. Now what we can do is convert the index equation that we are given into a log equation. Then we let p equals to log base 5 of x. So we will get p equals to square root of 2 plus 4 times 1 over p. Since if we use the reciprocal law, log base x of 5 is 1 over log base 5 of x. Now if we square both sides, this is actually a cubic equation once we multiply by p throughout. And it's a nice cubic equation that we can factorize. We'll see that 2 cubed minus 2 times 2 minus 4 equals to 0. You can see that p equals to 2 is a root. So this allows you to factorize out the p minus 2. And we'll get either p equals to 2 or p squared plus 2p plus 2 equals to 0. Now, the quadratic cannot be solved. You can see that it's clearly greater than 0. You could complete the square, or you could just observe that since p squared plus 2p plus 1 is a perfect square, the right hand side, this quadratic has to be greater than 0. So there are no roots there. So we let p equals to 2. That tells us that log base 5 of x equals to 2. And we can convert the log equation back into its index form. So x is equals to 5 squared. And the final answer is 25. So did you get the answer? Question 5. Given that log base 2 of 49 whole things squared plus 4 times log base 2 of log base 3 of y whole things squared equals to 4 times of log base 2 of 49 multiplied by log base 2 of log base 3 of y, find y. So pause the video here and give this question a good try. Now this looks quite convoluted, but we can simplify this a lot by just letting p equals to log base 2 of log base 3 of y. This simplifies the equation down to this, and if we bring the right-hand side over to the left-hand side, notice that what we get is a squared minus 4ab plus b squared kind of expression on the left-hand side. It's a perfect square, so we can factorize it. This gives us a minus 2b squared, which is log base 2 of 49 minus 2p squared, meaning that log base 2 of 49 minus 2p equals to 0, or p must be half of log base 2 of 49. And we can bring the half into the power of 49 because of the power law, and this will give us log base 2 of 7. So we just have to replace the p. So the p is log base 2 of log base 3 of y is equals to log base 2 of 7. That means log base 3 of y is 7. So we can convert the log equation back to the index equation. Y will be equals to 3 to the power of 7, which is 2187. And that's our final answer. So did you get the answer? Question 6. How many prime numbers p satisfy the inequality modulus of 2 log base 3 over p of 3p squared greater than 3 over 2? Pause the video here and give this question a good try. So the first thing we can try to do with the left hand side is to do a change of base. So we're going to do a change of base to base 3. And you'll see that we have log base 3 of 3p squared in the numerator. We can apply the product law, and we'll split it up to log base 3 of 3, which is 1, and log base 3 of p squared. We can take out the square to a coefficient of 2. For the denominator, we can split it using the quotient rule. This is what we'll get. And then we can combine the 2 and the fraction. We'll make a common denominator. And this is nice because the logs in the numerator will cancel out. This tells us that modulus of 3 over 1 minus log base 3 of p is greater than 3 over 2. Now we're going to split this into two cases. What happens if log base 3 of p is less than 1, and what happens if log base 3 of p is greater than 1. We don't have to care about log base 3 of p equals to 1 because that will cause the denominator to be 0. So in the first case, we can see that if we bring the log base 3 of p over to the right hand side, then 1 minus log base 3 of p will be greater than 0, meaning that our modulus would be positive. So we can remove the modulus and cancel the 3 on both sides. Simplifying this inequality gives us log base 3 of p greater than negative 1. And I can make p the subject. P will be greater than 3 to the power negative 1, or 1/3. So in case 2, we consider log base 3 of p greater than 1. This tells us that the denominator, 1 minus log base 3 of p, is less than 0. So when we open up the modular sign here, we have to be careful and reverse the terms in the denominator to turn it to positive. So we'll get 1 over log base 3 of p minus 1 greater than half. We can simplify this further, and we will get log base 3 of p to be less than 3. In other words, p is less than 27. So if we count up all the prime numbers, we would get 9 answers. But is this correct? So here we have to check. Are all these values of p possible? Because the number 3, if we substitute it into the original question, we'll get a base of 3 over 3, which is 1. You cannot take log base 1. So we have to reject 3, meaning that there's only 8 answers. So did you get the answer? Question number 7. Find the value of 2 plus log base 2 of 3 over 1 plus log base 2 of 3 plus 3 plus log base 3 of 4 over 1 plus log base 3 of 2. Pause the video here and give this question a good try. So we're first going to simplify the two fractions. Notice that we can split the 2 in the numerator into 1 plus 1, and the 3 in the second fraction, we can split it into 1 plus 2. And for log base 3 of 4, I can simplify it as 2 log base 3 of 2 using the power law. Now, in this red rectangle, I can divide the numerator by the denominator to get 1. And in this second red rectangle, I can divide the numerator by the denominator to get 2. So 1 plus 2 is going to give me 3, and I'm left with these two fractions, and I'm going to combine them as a single fraction. So after combining it, notice that in my numerator, I can simplify it to get 2 plus log base 3 of 2 plus log base 2 of 3. For the denominator, after I've opened up the two terms and expanded it, I'm going to get a log base 3 of 2 times log base 2 of 3. And if we use the change of base law, we can simplify it as ln 2 over ln 3 times ln 3 over ln 2, and that gives us 1. And in the denominator, the 1 plus 1 is going to give us 2, and you'll notice that the numerator and denominator is going to be the same. So we can simplify that. It will just give us 3 plus 1, and that answer is 4. So 4 is our final answer. For question 8, with a multiple choice question, we are given that x is equals to 1 over log base 1/3 of half plus 1 over log base 1/5 of 1/4 plus 1 over log base 1/7 of 1/8. So which of the following inequalities is true? Pause the video here and give this question a good try. So the first thing we can do is we can apply the change of base law, and we're going to change it all into the ln. So log base e. This is what we'll get. Now we can further simplify this because ln of 1/3 is the same as negative ln 3. Ln of half is the same as negative ln 2. So if we can remove all the reciprocals, we'll just get ln 3 over ln 2 plus ln 5 over ln 4 and ln 7 over ln 8. Now notice that in the denominators we have 2, 4, 8, which are all powers of 2. So we can simplify that using the power law. Ln 4 will become 2 ln 2. Ln 8 will become 3 ln 2. And we can combine these three fractions together as a single fraction. The common denominator will be 6 ln 2. And our numerators will be 6 ln 3 plus 3 ln 5 plus 2 ln 7. Now we can use the power law, and we can change this 6 ln 3 into ln 3 to the power of 6, and further apply the product law and combine it as a single logarithm in the numerator. This will give us ln of open bracket 3 to the power of 6 times 5 to the power of 3 times 7 to the power of 2. Now this is not easy to compute, but we don't need to get a precise answer for x, we just want an estimate. So what we're going to do is we're going to approximate 3 to the power of 6, which is 729. We're going to approximate it to be 720. And 5 to the power of 3, we can keep it as 125. And 7 squared instead of 49, I'm just going to estimate it to be 50. So this is nice because it's easier to compute. Of course, if you want to actually calculate that in an Olympiad setting, it's not impossible either. You will get 4.5 million, so log base 2 of 4.5 million, and I split the 4.5 million into 4.5 times 10 cubed times 10 cubed. Why 10 cubed? Because 10 cubed is 1000, and it is very close to 1024, which is 2 to the power of 10. This allows me to estimate that it would be somewhere between 2 to the power of 22 and 2 to the power of 23. And since we're taking log base 2, we'll end up with 22 over 6 and 23 over 6. So we know that x is roughly between these two fractions. So x must be between 3.5 and 4. So option E fits the best. So were you able to get option E as well? Question 9. Find the smallest positive integer k that satisfies this inequality. Pause the video here and give this question a good try. Now the first thing we can do is we can apply the reciprocal law, and this is what we're going to get for our inequality, and it looks almost nice. We wish that if we apply the product law, you see you'll get 3 to the power of k times 4 to the power of k times all the way to 2015 to the power of k If only that would give me 2015 factorial to the power of k, but we are short of 2 to the power of k. So since we're short of it, let's just add it in and subtract it away. That way, these terms in the blue box, if we apply the product law to it, will give us log base 2015 factorial of 2015 factorial to the power of k. But we still have some stuff left over. We can apply the power law here and take out the k, and we can factorize out the k and simplify since log base a of a is 1. Now notice that what we have is 1 minus log base 2015 factorial of 2 is very, 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 very close to 1. It's just slightly less than 1. So we are taking some number k and we're multiplying by 0.999999, and it needs to be greater than 2015. So this number has to be the next integer after 2015. It will have to be 2016. So did you get the answer? Question number 10, and this will be our last question for this episode. Find the value of a for which the function y equals to log base a of x intersects its inverse function at exactly one point where a is greater than 1. Pause the video here and give this question a good try. First, let's graph our log function y equals to log base a of x, and then our inverse function y equals to a to the power of x. Now, if the two graphs intersect at only one point, these two graphs must be tangent to each other, and that tangent also has to be that line of symmetry, which is y equals to x. So at x equals to c, y would also be c, and at this intersection point, c comma c, c will be equals to a to the power of c. And if we make a the subject, a will be equals to c to the power of 1 over c. We know that at this point, the gradient is 1. We need the gradient function, so we need to differentiate. And it's always easier to differentiate if it's base e. So we convert the equation y equals to a to the power of x, we'll change it to y equals to e to the power of x ln a. This is easier to differentiate. We will get a to the power of x ln a. Then we'll let x equals to c and let the gradient be 1. Next, we can rewrite this because a to the power of c is equals to c, and a is equals to c to the power of 1 over c. So if we substitute away the a, notice that this equation in c, we can cancel the c with the power 1 over c using the power law in logarithms. That tells us that ln c equals to 1, meaning that c is equals to e. So if we sub that back to find a is equals to c to the power of 1 over c, so a is equals to e to the power of 1 over e. So that will be our answer. So our final answer is e to the power of 1 over e, which is approximately 1.44. We have come to the end of lecture 1a. So if I make a 1b, it will feature more logarithm problems. And if I get started on 2a, we will go into some Trigo Olympiad problems. So do leave a comment down below if you have any senior section topics that you would like me to expand more on. And thank you for your kind attention, and have a great day of learning.